Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Luca Morricone of EOS and Nir Sever of Protantex. I'm going to talk today about using deep data to improve reliability testing. Nir, what sort of problems are you trying to solve with deep data? What are you seeing out in the market?
We've been doing reliability testing. I've been myself a project manager for many years, and the way reliability testing was always done was you take a batch of devices, you test them by running your test patterns, and then you put them in the oven for a certain amount of hours. After a certain amount, you take them out, and then you just rerun the same type of test. And you do that, we call them stations. They are standard stations, and after 1,000 hours, I'm talking about HTL, if your last readout gives you a good result, then you say that your device has passed qualification. And if not, usually you scratch your head, and the remedy was either you find something and you have to start it all over. What we were always lacking are a few things. First of all, is no quantitative data during the test. So you know that they are passing or failing. Assuming you are passing, you still don't know how much they have degraded, how far you are from the failing point after your last readout station, or if halfway through the test it was still passing, and then the next time it is failing, you don't know what was the rate of failing. So instead of having quantitative data, you're limited to a pass-fail. The next thing is that the whole concept of stressing, and then you take the devices out of the oven and test them, so stress then test, there is actually some recovery. So devices will recover a little bit when you take them out. So in fact, you are not stressing them to the level you wanted. So stress then test is not the optimal way.
And how do you describe deep data? What is that versus other kinds of data?
So deep data means that we can mine performance and health data from within the semiconductor itself, anytime when the device is running structural tests or when it's running a functional test, either on the tester, on a board, or even in mission in the field. So that's deep data, and the data is used to field algorithms. So algorithms running either on a cloud or on the edge, for example, on the tester itself, can actually use the data interactively and can provide insights and can direct you for actions to be taken and provide root cause analysis if you have some issues that you are not expecting. So deep data is something that comes right from the semiconductor. These are measurements taken from within the chip and then processed outside.
So Luca, what does EOS do, and what sort of problems were you running into?
With modern system on chip, reliability tests come into let me say, different kind of problems, because most of times with this complex architecture, it's not easy to guarantee the right stress level for the chip and to understand if you are stressing correctly. And also, it's difficult to have a complete detection on a reliability test platform, because all the testability of the device is arranged for a standard approach on ATE. So in this case, you have all the input and outputs completely available for your test. While we're performing stress on a massively parallel test, you don't have this chance. So first of all, device testability is one of the key points, and is also one of the weak points in order to have a complete reliability assessment. Okay, so this is a great problem. And also, the other aspect is usually customers with a complex system on chip use structural tests like scan and TPG in order to stress, but we found that no specific metrics for the stress phase were in place. So basically, it's hard to say if you are stressing in a correct way. So we were looking for a solution in order to overcome these aspects, these problems, okay?
Does it become more challenging to do these tests as you get into advanced packaging, 2.5D, 3D, as well as some of the advanced nodes?
Yes, of course, increasing the integration of the system on chip, so going towards very small geometries, and with the introduction of advanced packages, all becomes more critical. And so, for example, also the interconnections, reliability of the interconnections is critical, and also the test phase and the stress phase is not already prepared for that. So we're wondering to find solution in order to have something more structured, more to introduce metrics on that regarding stress and detection of possible issues.
Okay, let's take a closer look. Nir, what are we looking at?
So what we are looking at is this concept that we are now proposing. What you see here is in the center is one of the typical high-end LSA reliability tester platforms. On the left-hand side, we are illustrating the fact that you are now using not just any chip, but a chip that is now powered by Proteantec's embedded in-chip monitoring, as well as structural test and functional tests. All that is now located inside the tester. The LS tester is doing a combined stress and test. And on the right-hand side, what we are showing is the data coming out and feeding into our software platform. And where we are illustrating two types of analytics. One is the cloud analytics, in which we can do post-processing for very large populations and run machine learning algorithms to find and provide a calculation for more advanced algorithms, as well as the on-tester analytics, which can provide immediate responses and alerts if we see something that is deviating from the expectation. Because one of the benefits is when you're doing this inline and interactively, you can immediately fix an issue or even stop the test and not just continue endlessly. 1,000 hours is 40 days. You don't want to wait 40 days to just see that something went completely wrong. So this will provide a real-time alert if you need to take an action and maybe take one of the devices out or fix the settings or restart a new batch.
And Luca, how did you put these pieces together? What sort of issues did you have in terms of you were working with standard ways of testing these products before, now you're adding in the analytics? How do the pieces go together?
Of course, we need to manage different challenges. Of course, first of all, we need to interface the technology that Proteantec have in order to, let me say, collect data from the device and then make this available on their platform. So to create the right software interface to exchange data, and then of course data volume. So all the management of data exchange, typical of the data exchange.
The challenge here is always integrating this data though, right? I mean, you now have data that you had before and you're trying to integrate it with a completely different type of data that's coming in online now with basically AI and ML as well.
Yeah, yes, of course. Data analytics is something that we, let me say, are used to manage with standard data. But of course, with agents, something different happen because those agents must be, let me say, in some way interpreted, okay? Because they take care of specific measurement and they are always linked to the technology that has been developed. So this is why we need to cooperate with Proteantec, because we need to, let me say, merge this in order to give to our solution the possibility to extend the feedback that we are able to give to our customers in terms of reliability assessment.
One of the challenges here is that as we start getting into this deep data, in addition to the other data, you have so much data coming from so many different places that you really have trouble sorting through it. How do you deal with that?
The trick is that we are doing a lot of processing of the data already inside the chip. So our agents are not just dumb monitors, I would say. They're actually very smart monitors, and we have a whole logic controller infrastructure that goes inside the chip and connects and processes the huge amount of data, and only compute and store for later processing what we believe is important, and that depends on the type of agent. So each measurement has a meaning in a context, and we keep set of data that is meaningful for later processing. So the fact is that the data is minimized already inside the chip by hardware, and then we pack it in a very compact way, and it is output through the interfaces and into our cloud platform. So the other concept here is that this is not just a regular or generic cloud analytics. It's cloud analytics populated with algorithms that know exactly how to process our data. Our agents were made for the analytics, and the analytics knows exactly what the agent produced. So all that means is by relatively small amount of data, we can provide a lot of meaning for the cloud analytics to provide you with the insights.
And Luca, from your standpoint, you not only have that data, you also have the other data that you were collecting in the past. Now you have to somehow combine that and figure out what are you trying to get out of this, right?
Yes, of course. We have to consider that the reliability test is performed in parallel on a huge amount of devices. In some cases, we can reach, for example, a parallelism in excess of 500. Okay, so we have to take care, of course, because in this architecture, we have lots of devices that runs in parallel. Okay, so of course, apart the data coming from agents, we have to also manage diagnostic information in case of failures. So we have, of course, to take care of this situation and put in place the correct, let me say, architecture in order to manage both.
You also have to integrate this not just with the data, you also have to integrate this with your own methodology and workflow, right?
Yes, of course. As we said, the target is to obtain the maximum stress and test coverage during reliability. So to gain this on a DFTI paralleling tester like ART, it's necessary to, first of all, to optimize device testability. We call this step design for reliability test. And we have to embed all the necessary IPs for an optimal failure triggering and detection of the different internal blocks. In this game, of course, agents, Proteantex agents, have an important role because with these agents, we have more visibility on what's happening inside the chip, on the performances, on aging, etc. Of course, test features are embedded in the chip. Test features are embedded inside the tester. We have also other possibility. We have the possibility to integrate some test feature also on test fixtures, okay, that we build for each application. Of course, the test platform have to manage different challenges because we have to manage very high accelerated factors. So we need to simulate the device as in final application, but in a shorter time frame. So usually HTML test lasts 1,000 hours, but in this 1,000 hours, we have to go above the typical application condition, both in terms of voltage and temperature.
So what sort of challenges are you facing when you're doing this? What you have a platform there, what does it have to do now that it didn't do in the past?
First of all, we need to work on the power supply subsystem because new generation ICs consumes a lot of power and they have very fast transients. So we need to manage a new generation of power supply platform. And then we have to bring on the market an architecture with dedicated test resources per device, because we need the right accuracy, the right quality during test, okay? Of course, the other aspects are related to the thermal management. We are now facing devices that during qualification dissipates up to 1,000 watts. So we need a very high temperature accuracy also for this kind of devices and at the extreme condition of the HOL. In this case, we develop a liquid cooling thermal active control, okay, in order to do this. And of course, we have to, let me say, manage also all the data acquisition capabilities. We have to increase our tester memory in order to capture more data, more failure signatures. And this is of utmost importance because we need those signatures also and those data also in real time in order to connect analytics at edge, like Proteantex solution. And the other aspect, we work on adaptive stress and test capabilities because we need to, based on agents' feedbacks, we want to tune this stress and test matrix. So we start with the test and stress matrix. We see through the agents if we are stressing according to the mission profile, and then we can adjust. We can adjust in real time the stress and test matrix. So these are the areas that we have to bring to a new level
So Nir, what does the data actually look like here?
As I said in the beginning, our data is provided through measurements that are taken by different type of agents. We have different type of agents that measure different type of things, and each one and the combination, we call it the fusion of the data, is what provides the insight. So few examples here. We start with, for example, a smart material selection and outlier screening. One of the challenges is that you don't want to skew your measurements because you have used an outlier device or an out-of-spec device. So starting from what we call classification and profiling agents, we can map every chip and every sub-area in the chip to how it was produced. And by that, we can, first of all, provide a proposal for selection of devices that are more useful, that they represent the entire distribution of the process parameters on one hand, and on the other hand, we can detect and mark devices that are out of spec, so they will not be used for this outlier detection. So we call this smart material selection. The other type of data is degradation data. So we have monitors that measure timing passes in very high coverage across the chip, and we keep measuring those remaining timing margins all the way through the stress and test. And by that, we can show the degradation rate. So, for example, what you can see here on the bottom is a different type of errors in the chip and different type of metrics and how they degrade during the test. So we keep tracking degradation, and the degradation is used to understand remaining a useful life, or to correlate it to mission profile, because again, Luca said before, mission profile is a very important aspect of reliability testing. You must test what the chip is going to do in real life, and this is done through the mission profile. But if you are not stressing the device to the mission profile, you're actually not testing it. So we can, through the data, through degradation data, tell you if you are stressing to the mission profile. The other thing is we're actually measuring the stress level. We have direct measurement of the stress level. And again, this is another input for a mission profile validation. We have environmental agents that measure things such as voltage levels and temperature levels and noise, that again will be used to understand if your setting is correct, if your degradation is as expected, and if something goes wrong, then this data is used for root cause analysis. We can pinpoint if one device or one area in the BIP, the board, is not suffering the same level of stress, and we can immediately feed this data for the operator to take actions, or for the interactive tester to fix the settings interactively.
Luca, from your standpoint, what does this do to the job of the test engineers? You now have to reconfigure the entire flow here because they're looking at this stuff in real time. In the past, it was, this failed, or we didn't get the yield that we wanted. Now we go back and fix it, and we understand where the problem is. Now you're looking at this as it's happening, going, okay, how do we keep track of all this data? How do we apply it so that we actually can improve the yield?
Now, with this integration, we have the possibility to move most of the activity that typically are performed in post-processing, let's say, during the directly on the machine and directly with the software, of course. So really, it's a new perspective, of course, because in this way we have also the possibility to check and modify also on fly and with defined metrics our reliability test. So we are not reactive but proactive. Okay, this is really important. Of course, we also have to manage, you are right, the way we are going to develop the test flow, of course, because when you come with real-time feedback, of course, you have different options available. And for sure, with art, since the beginning, was fixed in order to manage possible option like adaptive stress and test. But till now, it was hard to find out the rules. Okay, now of course, with testability, device testability, and especially with agents, we have great options for that. And so it's something that will for sure change, have a big impact on also on how we approach the reliability test, the development of the test program, and also all the analysis, of course, of the data.
Look, as we're building on what you were just saying here, you're really redefining the entire flow, how you enter into the picture, what your engineers do. It's a much different way of doing that. And that's not a trivial change for a lot of companies, right?
Yeah, of course, what we are bringing on the market is for sure something that has the target to overtake the issues that typically a reliability engineer have. Basically, they have to deals with different spreadsheets, Excel spreadsheet, to evaluate the stress matrix, to evaluate if the stress is okay, is adequate versus mission profile. Now, I can say that with such kind of instruments, on one side, the work is easier. On the other side, it means that we have to change the process that we are usually apply to the development of the products. Okay, so we have to think to this, since design stage phase, we have to embed all the right IP for testability. We have to insert agents, but then once you have done this, it's all more easy. And this kind of approach is, of course, now, let me say, in line with the silicon life cycle management that nowadays is the new approach in order to, let me say, solve different issues, not only the issues related to the testing, but also production on field, monitoring on field. So basically, it's something that can be embedded from our customers also in a standard way. I see that in now we have all the environment that is ready to apply this new approach, because it's not only something that is needed for the reliability, but it's also needed for testing and on-field monitoring. So we have the chance, really the chance to do this this change with relatively minimum impact.
And Nir, this really has to start at the architectural side of a chip design, right? Because you really need to build all this data at the agents in order to collect this data into the chip so that you can actually do what Luca's talking about here, right?
Yeah, you're right. So, you know, 6 years ago when we started deploying this solution, first it was hard, but then it was strange. But nowadays, I'm happy to say that, you know, we have so many dozens and dozens of customers that have successfully implemented our solution. They came to realize that nowadays with advanced electronics and advanced applications, you can no longer have, you know, zero visibility into what's going on inside your chip. And that's reliability testing is one, but production testing, characterization, but also how the chip operates in the field, all that requires data. So deep data monitoring is now becoming kind of a standard feature for advanced electronics, especially in mission critical application. No architect will now dream of producing an architecture that does not include in-chip monitoring. So now it's more easy than it was 5 or 6 years ago when we started. We also evolve a lot. So we've came with a whole set of EDA tools that help manifest the analysis of what type of monitoring you want, how to put them, where to put them, and actually help you with the process of implementing those agents inside your chip. So everything is now very well automated. There is much less friction. And so we see our customers are really implementing and deploying this system in a wide variety of applications nowadays.
Nir Server from Protantex, Luca Morricone from AOS. Thanks for your time. Really interesting discussion.
And thank you very much, Ed, for the questions.
Thanks a lot, Ed.